I don't know what's the time that you are watching the video, but from my side it's good afternoon. It's almost going to be 5 here at IIT Kanpur when I start this talk, the 6th talk of the series of the program and the first talk of the second week. And today we are going to speak on higher dimensional Euclidean spaces. Higher dimensional Euclidean space. We have been speaking on the spaces of 2 dimension and 3 dimension. These are spaces of our own experience. So how can I construct a space which has a higher dimension? How do I construct a space which has a higher dimension? See, let me tell you that a lot of things in mathematics can be gauged through intuition. For example, we have studied the spaces R2 and R3 and R2. So everything is actually built up from a set of real numbers x1, x2, where x1 is in R and x2 is in R. So this is what we have studied, and this can also be written as the Cartesian product. This is called the Cartesian product of R with R. Now talk about R3. So now it has 3 coordinates to represent the point. That is our space of our own dimension, own experiences. So here x1 is element of R, x2 is element of R, x3 is element of R. So these are my standard spaces R1, R2, R3. R1 is R, so R3 is the Cartesian product of R with R and with R. In another sense, it is the Cartesian product of R2 with R. How can I improve upon this and make a higher dimensional space? To make a higher dimensional space, I just have to take a little leap in the imagination and consider an n dimensional space Rn. So what I am going to write, n dimensional Euclidean space. So that is denoted as Rn, whose consists of vectors x, which I call vectors because anything R2, R3, everything consists of vectors as we have already studied, x1, x2, and it has n real numbers as its components. It is represented by a tuple of n real numbers, n tuple. So this is sometimes called an n tuple, and where each of these xi's are element in R, where I runs from 1 to n. So what is Rn in terms of a Cartesian product? It is n-fold Cartesian product of R. So Rn can be written as R cross R cross R is called the n-fold Cartesian product. N-fold Cartesian product. And this also symbolically sometimes written as the sign of product is this product of sets, Cartesian product of sets. I is equal to 1 to n Ri, where each Ri is equal to R for all I. You can write it like this also, but this is all right. So it is just a Cartesian product. So what is R2? So basically you take any x1 here and any x2 here, you know, just draw perpendiculars, and this x1 x2 is in R2. So, this kind of formation of tuples is called a Cartesian product. So, now you might ask that, okay, when we are in our existence, spatial existence, that is when we are in our familiar world of length, breadth and height, we understand where we are standing, we can touch this board, you can touch the ground, I can understand, you can touch the side of the room, but what about having such an abstract space? Does it really fit in? Does it really help us in our understanding of the physical world or anything relevant to do with humankind? The answer surprisingly turns out to be yes, because one of the first examples that I show you where I go beyond the third dimension is special relativity of Albert Einstein. In special relativity was developed because Einstein was trying to see in his special relativity how good are Newton's mechanics and theory of electrodynamics of Maxwell's equation of electromagnetic waves, how are they compatible, and he found that they were not compatible. And in order to make a system of dynamics where the electromagnetic theory is compatible, he invented what is called special relativity, in which he had these kind of assumptions that we will talk about inertial frames, which we will not get into the details, and nothing in this universe moves at a speed higher than the speed of light in vacuum, which many of us know is denoted as c. Now, in special relativity, idea of time and space is actually separate entities, which what we learned in mechanics, because we had also dealt with applications to mechanics of these ideas of vectors. So, those in special relativity, the idea of time and space being separate entities is washed away, and a single entity called space time is studied. And in order to study the geometry of the space time, you need a coordinate system where every point is denoted by 4 coordinates, a time coordinate and 3 spatial coordinates. So, here you see, you immediately in understanding, better understanding of a physical theory, you need 4 dimensions. Another application where you might need 20 dimensions or 20 or 50 or millions of variables, millions of such x1, x2, xn's, is a field called linear programming, and that has got nothing to do with the physical world, but more with the human world that we live in. It is an area of optimization, and I will give you an example through which you will see why this structure of Rn, this abstract space, becomes interesting and important in our day-to-day scenario. We will introduce to you what is called the diet problem. So, this was a problem used for US Army, what amount of diet I should give to a soldier. Suppose I should give them good amount of proteins and good amount of vitamins, right. So, let me see. So, I have 3 nutritional things that I want to give, proteins and say protein and vitamins. These are the 2 things I want to be very careful about, protein and say vitamins. And at every meal, at lunch, I am giving them 5 different kinds of food, or maybe in the whole day I give them 5 different kind of food. So, food 1, food 2, food 3, food 4, food 5, food. And this is the proteins and vitamins, this is called the nutrients. And these are the levels. So, suppose for the protein, the first one has A11 amount of protein per unit, the second one has A12 level of protein per unit, the third food has A13 level of protein, fourth food A14, the fifth one A15. Similarly, A21, A22, A23, A24, A25 shows the various levels of vitamins in various nutrients per unit quantity. Now, so the minimum level of protein I required, an army say and soldier requires is C1, and the minimum level of vitamins he requires is C2. So I have to now I have to determine how much quantity of the foods I should give to a soldier so that my cost is minimized, but at the same time I maintain his protein and vitamin levels. So let P1 be the price of the food 1 per unit, P2 be the price for food 2 per unit, P3, P4 and P5, these are all greater than 0. Now X1, X2, X3, X4, X5 is the amount of food, the amount of the first food, amount of the second food, amount of the third food, amount of the fourth food, amount of the fifth food that I need to give to the soldiers. Z is the total cost which I need to minimize. So if this is the levels I should give, my cost is P1 into X1, total cost is P2 into X2 plus P3 X3 plus P4 X4 plus P5 X5. So I need to minimize this cost, but I have to make sure that the soldiers get their level of proteins and level of vitamins, minimum level of proteins and vitamins, so that the amount of protein if I give him X1 amount of food, the amount of protein I give him is A11 X1. Similarly, A12 X2 plus A15 X5, and this total protein has to be minimum C1. Similarly, this is the amount of vitamins in various total vitamins that I have to give. A25 X5, but this has to be greater than C2, the minimum requirement. And of course, the amount of food that you will give, the amount of quantities of various foods that you would give has to be non-negative integer. Sorry. X4 greater than or equal to 0, all of them are non-negative. So this, what I have written down, is called a linear programming problem, and it has a huge amount of applicability in business, in economics, in actual army operations. So this thing as a whole, this linear programming, the interesting part is that this problem could be solved algebraically, and it was first solved, a beautiful, very easy approach, though with some cumbersome algebraic manipulations, was given in 1947 by George B. Danzig, sometimes called the father of modern optimization. So George Danzig had solved this problem. So you see that I could have 5 foods, so it could be 5 food, it could be 10 food, it could be 15 food that you give throughout the day. It could be 20 food, it could be 30 food, it could be, I do not know how much amount of food that you give. So per unit of food, this is the amount of proteins, 1 gram, 2 gram, 3 gram, whatever. So this problem is a very important problem called the diet problem, that is actually used by many hospitals in the world. It is part of health economics also. And this diet problem has recently been used by economics to talk about poverty line. So that's the kind of thing that this interestingly small problem can do. Now let us come and see how we look at vectors in Rn. What do I mean by vectors in Rn? So, given any vector x, I will just write it without the arrow, can be represented as a element which has n coordinates, right. So, it is called the n tuple. Now, you can also talk about a vector in Rn. You can write an A vector, and if this A vector has coordinates x1, x2, xn, then I suppose it has this coordinates x1, x2, xn, or say a1, a2, an, if you want to write it vectorically. See, we will always write vectors as column vectors, but sometimes we can use it as row vectors, because you see here we have written them as row vectors because for convenience of writing, nothing else. So, you can write them as this form. Once you know that these are coordinates, it can be written as a1 e1 vector, a2 e2 vector, an en vector. So, when I write x, I will not put the ix, I will mean just an element of Rn, I will not put the vector, I will understand there is a vector. So, if you want to write it just like a vector in physics, then you write it like this, and where each ei is a vector 0, 1 at the ith position and 0 everywhere. This is called the canonical, this e1, e2, en, this set of vectors form the canonical basis or the standard basis of the space Rn. So, basically they are replacement of the 1 0 0 1 and 1 0 0 0 1 0 and 0 0 1 vectors that you know in R2 and R3. Now, given two vectors, say x and y, x is x1 to xn and y is y1 to yn, then the dot product, see when I am writing x and y, these sort of things, I will not put the vector sign on the top, but when I am writing a, b, the standard vectorial notations, I will put the vector sign on the top. So, if I am talking about, so this is the distinction, the style of writing I will adopt, but when I am writing x is x1, x2, xn, x is actually a vector. So, how do you define the dot product of x and y, that is x dot y? X dot y is same as what we learnt in R2 and R3, but now you just extend it to Rn. So, once a dot product is defined, can the idea of the Cauchy-Schwarz inequality be very far? So, let me write down this. So, given a vector x, what is the norm or the length of the vector x? So, given the vector x, what is the norm length of the vector x? Length of x, or also called the norm of x, that is given as norm of x is square root, this is sometimes called the Euclidean norm. So, we bother at this point only with the Euclidean norm. At this level you do not need to bother about anything else. This is exactly an extension of the Pythagorean theorem to n dimensions, and this is exactly what you have learned in 2 dimensions when you put n equal to 2, or 3 dimensions when you put n equal to 3, and you have just extended it. The geometry of 2 dimensional spaces, when you look at it from a geometry, absolutely pure geometric point of view, is very different between 2 and 3 dimensions, because for a 2 dimensional space these 2 lines are parallel only. If there is a sheet of paper, then these 2 lines are parallel, but in a 3 dimensional space these 2 lines are also parallel, it is called skew parallel. So, from a pure geometric point of view there is a difference between 2 and 3 dimensional space, but if you just look at from the algebraic point of view, then it is exactly that's kind of you just do the algebra. So, it is whatever you do for 2 can be repeated for n. So, and that is exactly the way the definition is extended. So, the Cauchy-Schwarz inequality So, the dot product of x dot y for any vector x and y is less than equal to norm x into norm y. This is a Cauchy-Schwarz inequality. Now, if x is equal to 0 or y equal to 0, it automatically holds because both sides will become 0. This is automatic holding. While, so how do I prove this? So, if I take the length of the vector, you know that length of this is a norm, it will follow all properties of the length. So, I am not writing the properties of the norm which you can easily figure out. I would like you to check out the properties of the norm, check the Wikipedia, never mind, check out the properties of norm. It is exactly the one you learned in, you see in 2 dimension and 3 dimension. Of course, norm can have various definitions. So, here, but here we will be using only this definition, the Euclidean definition. This is what we are set to prove. So, you know that norm of x by norm x. So, x is a vector, I am multiplied by 1 by norm x. So, now I am taking x and y both not equal to 0 vectors. So, none of them has length 0. So, I can divide them by, so I can 1 by norm x is a number which I can multiply, scalar multiply with the vector x. The norm square of this is equal to, is greater than equal to 0. So, obvious. And now you do exactly what you do in the case you know in 2 dimension and 3 dimension. It will be the same kind of expansion, norm x square by norm x square minus 2 x dot y norm x norm y plus norm y square by norm y square. So, this is 1, this is 1, and I would like you to check the calculation. So, it will be norm of this whole square. So, then 1 by norm whole square will go out and this will be norm x square and they will cancel, and you will have 1 minus 2 x dot y by norm x norm y plus 1 is greater than equal to 0, which will simply tell me that if I collect the 2 and keep it here and take it on the other side. So, I will have 2 is greater than 2 of x dot y by norm x into norm y. So, if I cancel, what I finally get is x dot y is less than norm x norm y. Similarly, let us take, if I put plus here, that is x by norm x minus y by norm y whole square. Now, this instead of minus I put a plus and put greater than equal to 0. Then doing the same kind of operation here, minus would become a plus. You would be able to prove that minus x dot y is less than equal to norm x norm y. So, what you have finally, if I combine these two, it will become x dot y is less than equal to norm x norm y and is greater than equal to from this minus norm x minus norm y. This simply means that the modulus of this is less than norm x into norm y. If a number lies between minus a and plus a, the modulus of the number is strictly less than a. So, that is what you, so x dot y, So, this is what is the Cauchy-Schwarz inequality. So, you have proved the Cauchy-Schwarz inequality. Once Cauchy-Schwarz inequality is proved, the triangle inequality cannot be far behind. So, we will now propose to prove the triangle inequality on this board, in this electronic board. And so, the triangle inequality again asks us to find, given a vector x and y, so x plus y, these are in n dimensions, is norm of x plus norm of y. So, now let us look at this expression, norm of x plus y whole square. So, this is equal to norm x square plus 2 norm x dot y plus norm y square. Now, applying the Cauchy-Schwarz inequality, I have norm x square plus 2 norm x norm y, this is less than equal to norm x norm y plus norm y square. Here I have applied the Cauchy-Schwarz, Russians obviously call it the Cauchy-Schwarz-Bunyakovsky's inequality, as I told you earlier. So, now here what I will get, this is nothing but equal to norm x plus norm y whole square. So, this implies that norm x plus y whole square is less than equal to norm x plus norm y whole square. Now, if you have two positive quantities or non-negative quantities whose squares of one is greater than square of the other, it implies the one whose square is greater than the number whose square is lesser. So, if a square is less than equal to b square and a and b are both non-negative, then a is less than b. So, here it implies that x plus y is less than norm x plus norm y, and as the French would say, we write it here as voila, that is done, and that is what we have as a triangle inequality. That is it, that solves the problem. Now, we are going to talk about matrices. Now, once we have spoken about things in n dimension, we are going to speak about matrices. So, what are matrices, and maybe I should write it on this board, and can we talk about a matrix of a given number of rows and given number of columns, and row and column need not be same. We are not talking about square matrix. We have spoken about square matrices and square matrices, and when we are talking about 2 and 3 dimensional spaces, we have spoken about 2 cross 2 and 3 cross 3 matrices, which we are now going to talk about m cross n matrices. So, m is the number of rows and n is the number of columns. So, where m and n, they could be different, one could be bigger than the other. So, how does the matrix would look like? So, we have such a matrix already when we wrote a linear programming problem. So, we had basically 2 rows because there were 2 nutrients and 5 columns there because there were 5 foodstuff. So, here the general way of writing it as A11, A12, A1n, A21, A22, A2n, AM1, AM2, AMN. So, this is an m cross n matrix. Okay. What happens? I can view that m cross n matrix A as a function from Rn to Rm. So, I can view it as a so called, it is the first step to view as a vector function. So, which carries one vector to another vector of one dimension to a vector of another dimension. So, basically I am looking at, by laws of matrix multiplication, what would be A of x. A of x, if I call each of these row vectors as R1, R2 and R3 and R4, then this Ax is nothing but R1 dot x R2 dot x, Rn dot x. So, how do I do it? This comes out of the policy of matrix multiplication. You have learned about matrix multiplication for 2, 2 and 3. So, same type of thing can be done. For example, here what will happen, this is Ax would be, so sorry M. So, it will be A11 x1 plus A1n xn, and the last would be, last component would be AM1 x1 plus AMN xn. So, this is nothing but the inner product of R1 into the x1 x2 xn vector. Now, if you look at it, you will immediately get some sense of what we are doing, some sense of matrix multiplication. So, I am trying to, instead of coming from matrix multiplication to this case, I am going from here to matrix multiplication. So, basically if you just have a vector, you take every row and take the inner product with that vector. So, suppose now instead of just a vector, I have a matrix which has some columns. So, basically what we have to do, we have to take the first column and do the same thing. We have to take the second column and we have to do the same thing. Let us see. I'll try to write it in a very simple way. So, let A be a m cross n vector. See, number of rows, number of columns in A and number of columns in B, a number of rows in B must match if I have to write down the product AB, n cross P say. So, I want to write AB. So, AB, what is AB? Or how I write down? So, A has m rows and n columns, right? So, just bother about the m rows of n, R1, R2, R3, Rm, and this has n columns B. So, column is written as C1, C2, Cp. Now, R1 is a vector in Rn and C1 is a vector in Rn, and they are, so what I write? So, what is my first, so what is the new matrix? So, I will have R1 into C1, R1, the next component is R2 into C2, R1 into Cp, the dot product, and the last row would be Rm dot C1, the same story I will write, Rm, so C will be changing, Rm dot Cp. So, now what is the order of this matrix? It is m cross P. So, AB is a m cross P matrix. So, any element of AB, if I take an element of AB and I write it as a Cij, I call every element of AB as Cij. Instead of Aij or Bij, I write it as Cij, where Aij is an element of AB and Cij is an element of Bij is an element of B. So, I can write this as Aij as a Mn matrix and B I can write as Bij as a NP matrix. And now, what is AB? It is, so what is Cij? So, how does Cij look? So, every Cij, let me write it down here, Cij is nothing but the inner product of the first row, right, Aik Bkj, where k is varying from 1 to Ai 1 to n, because k denotes the column of A and k denotes the row of B and they must be n here. So, that is one way of writing, and but the simplest way of looking at is this one, through the dot product. That is exactly what happens. Now A as a function or a vector function from Rn to Rm, this is a standard notion of a function. There is an input in Rn, the output is in Rm. So then A of x, A becomes what is called a linear operator. A becomes behaves like what is called a linear operator. So let us see what is the property of the linear operator. So A of x plus y, so linear operator has two properties. Number one, A of x plus y is Ax plus Ay. Number two, A of alpha x is equal to alpha Ax, where alpha is any real number. There are certain other issues about matrices which I do not want to get into too much in detail right now, but you might be wondering how to compute determinant of a square matrix if I had one. Determinant is only computed for square matrices, please understand. So if I have a matrix say of 4, so A11, A12, A13, A14. So A21, A22, A23, A24, A31, A32, A33, A34. See, A41, A42, A43, A44. Now how do I compute the determinant of this matrix? It is the same way, keeping the same plus minus alternating sign on. So if I go by the first row, A11 into the determinant of this matrix. So this matrix, which starts with A22 and ends with A44 in the diagonal, and that is the matrix obtained by taking away the first row and the first column, that is called into the determinant of A11. So A11 is the matrix obtained from the main matrix by taking away the first row and the first column. So it is called a kind of adjoint matrix. So this is so its first term is A11 into A11 minus A12 into, and A12 is the matrix obtained from the original matrix by taking away the first row and the second column, plus then the same thing this is how a determinant is calculated. There are several other things which is associated with a matrix which I do not want to speak at this moment. Let me just come to the end of our discussion today. So you have seen from the beginning, to summarize, that why I need to bother about n dimensions. N dimensions, it's not that mathematicians are just playing a game, oh let us just put n dimensions and let us play with it. It has applicability. The idea of n dimensions makes sense when we saw the dyad problem in linear programming, and hence all these type of things, which these extensions from 2 and 3 dimensions to n dimensions make sense, because all this can be used. Now of course, if I ask you what is the angle between two vectors in n dimension, two vectors x and y, it is nothing but the cos inverse of x dot y by norm x into norm y. So it is the same thing that repeats itself. Now here you also saw that in our physical theories we are talking about space time, all modern physics uses special relativity, and so we have to talk in terms of the 4 vector. This is what physicists call the 4 vector. So you have some idea about matrices now of the type m cross n, how to do their operation of multiplication. Addition on I am not telling you, you should be able to add, just they are adding the corresponding stuff. Means when you add two matrices, the number of elements must match to add. Basically you should be able to add the first row elements with the first row elements, second row element with the second row elements, right. So but when you come to multiplication, right, so when you come to, so you have two m cross n matrices, you can add them, right, because you have same number of rows, same number of columns. But you have different rows and different columns, then okay, fine, then that becomes very difficult, that then addition is not defined. So there are certain things which I have left out, addition, multiplication, which you can really figure out for yourself or for books, because certain things you also have to think about. Because why I suddenly just spoke about matrix multiplication, because matrix multiplication would become slightly important as we go on. So overall, we are now in higher dimensional space. So here we are going to talk about, many of our examples will consist of function of 2 variable, 3 variable, maximum 4 variable, but our theory would be with n variables always. So theory would be done in the most abstract form, the most general form, while examples, because they need much less time, if you ask me to do an example with 50 million variables, I can't do by hand, or with even 50 variables I can do by hand. So to do something by hand, we need to do it with 2 or 3 variables. So examples would be 2 or 3 variables, while our theory would be absolutely general, and that's exactly the point I want to stress before I end this lecture, that we are getting into absolutely proper multivariable calculus. We'll start about function of 2 variables, function of n variables, and its associated issues like partial derivatives, higher derivatives, Taylor series, maxima, minima, and all these things would gradually come up. So thank you once again for listening to me, and I hope I am being able to give you some idea of what good analysis means. Thank you very much.